Hi, Math 20s. This is the second lesson of logic. So up at the top it says inductive reasoning, validity, and counterexamples. So yesterday, or last day, we would have been talking about inductive reasoning and conjectures and kind of a little bit of the process that it is to write a conjecture based on patterns that we can observe. And so we've seen kind of some of the problems with that. So we'll do a little bit more conjecture stuff today and start to look at when our conjectures are wrong, kind of what we need to do. So the first one here, it says consider the pattern of multiplications. So if I take 1, 2, 3, 4, 5, 6, 7, 8, 9 and multiply it, that's what the little dot again is indicating, multiply it by 9. Oh, I don't have pen on. Multiply it by 9 and then multiply it by 1, it's equal to that number 1, 1, 1, 1, 1, 1, 1, 0, 1. I didn't say enough. If I take that same number, 1, 2, 3, 4, 5, 6, 7, 8, 9, multiply it by 9 and multiply it by 2, this is the next number. Then take that number, multiply it by 9 and multiply it by 3, I get that number. So you might also want to verify that and make sure I'm not pulling a fast one on you and saying that something multiplies to be equal to something and then it doesn't actually. But this one actually does work, so you can double check for me. So it says use this information to make a conjecture just about what you see with this pattern. And so this one, it's going to be less wordy than some of the stuff that we were doing last day. So I'm going to say if I take the number 3, 4, 5, 6, 7, 8, 9. So that's 123,456,789. And I multiply it by 9, and I multiply it by a number. This is me kind of really simplifying the conjecture process. It will be equal to whatever that number was 8 times. Six, 7, 8, and then a 0, and then that number again. So again, this is a number. So same number in all those spots. So again, here I'm multiplying it by 1. I have 8 ones, a 0, and then another 1. This time I'm multiplying by 2. I have 8 2s, a 0, and then another 2. Recognizing that I have 3. I have 8 3s, a 0, and then another 3. So this is where my conjecture is coming from. So if I take that number, multiply it by 9, and then multiply it by a number, the answer will always be whatever this number is, 8 times in a row, then a 0, and then that number again. So it's going to show 2 more examples that demonstrates your conjecture. So the one thing is, don't just write what you think should be happening. Make sure that it actually does it. So I'm going to try 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9 times 4. And 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9 times 5. So punch both of those into your calculator separately and see what you get. You might need to pause and press play now. So that one. Hopefully I counted right there. So trying both of those, again, double checking your calculator that I'm not, just writing that it works. So it says provide a counterexample to show your conjecture is false. So obviously I wrote my conjecture in a way that it was going to work out false. So I can find 1, 2, 3, 4, 5, 6, 7, 8, 9, multiplied by 9, multiplied by 12. So now the value is 12. So based on the way I wrote the conjecture originally, my number is 12. So it should be 12, 12, 12, 12, 12. Okay, so that's not going to work out. So if I multiply it by 12, what I get is 1, 3, 3. Uh-oh. I think there's 9. It might only be 8. Yes, it will only be 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this doesn't follow the way that I originally wrote that conjecture, that if I multiply it by a number. So what I could do is I could revise my conjecture to say only single digits. Okay, a single digit number. So it only works for 1 through 9. So just the way I originally wrote the conjecture. Sometimes we'll have something called a counterexample. So what a counterexample is, we defined that before, but it's an example that shows that a conjecture is not actually true, because it's not true in all cases. So Francesca was asked to make a conjecture about the difference, and the word difference, we're talking about subtraction, between consecutive perfect squares. So consecutive means one after another. And perfect squares, so a number multiplied by itself. So 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. So these are perfect squares. So she looked at 2 squared, again, difference. So 2 squared subtract 1 squared. So 2 squared is equal to 4. 1 squared is equal to 1. Okay, I did both of those there. And so the difference between those is 3. And then she tried 4 squared, which is 16. Subtract 3 squared, which is 9. So 16 subtract 9 is 7. And then she said, yeah, let's go further. Let's try 9 squared. So 9 multiplied by itself is 81. Subtract 8 squared, which is 64. So 81 subtract 64 is 17. So the conjecture that she made is the difference between consecutive, okay, so again, looking back at the sentence, the difference between consecutive perfect squares is always a prime number. Okay, so 3, so again, prime number has exactly 2 factors, right? 1 and itself. So, no, 1 is not. So 2, 3, 5, 7, 11, 13, 17, 19, and so on, and so on. So 3 is a prime number, 7 is a prime number, 17 is a prime number. So based on the examples that she chose, her conjecture makes sense, right? The difference, indicating subtraction, between consecutive perfect squares is always a prime number. So yeah, based on the examples that she chose, that does make sense. But it says, find a counterexample that invalidates this conjecture. So we could try something like 5 squared subtract 4 squared. So 5 squared is 25. Subtract 4 squared is 16. So that's equal to 9. 9 is not a prime number. So our conjecture is not true. So a revised conjecture, so something we could write the difference between consecutive perfect squares. Well, now we can write a new conjecture. Again, this is kind of our guess, so we don't know if it's true in all cases, but based on the evidence that we have, we know hers was false. So we could write a new one, just recognizing from the now 4 examples that we have, 1, 2, 3, 4. So based on the 4 examples that we have, we could say the difference between consecutive perfect squares is an odd number. Okay, so as of right now, as of all of the pieces of data that we have, so we have 9, 17, 7, and 3, those are all odd numbers. So again, we can't prove that a conjecture right now, we can't prove a conjecture, but based on the information we have, that's what we assume to be true. Okay, so in each case, a conjecture is given. Provide one example which supports each conjecture and one counterexample which shows the conjecture is false. If you can find any counterexample, the conjecture is invalidated. So if you can find even one, it means that conjecture is not true and either needs to be rewritten to kind of add in that piece of information or just kind of blown away. So it says the sum of 2 consecutive prime numbers is even. So again, we want to come up with something that supports it. And then we'll look to see if we can find a counterexample. Okay, so the word sum means addition, 2 consecutive prime numbers. So 2 consecutive prime numbers, so I wrote some on the last page. So 3 and 5 are consecutive in that they're the prime numbers that are one after the other. So again, prime numbers. So if I took 3 and 5, yeah, that's equal to 8. So that's even, okay? If I took 11 and 13, so again, consecutive means one after the other. 11 plus 13 is 24. That's an even number. So a counterexample, though, if we can see if we have one, if I actually take the first 2 prime numbers. So 2 plus 3 is equal to 5. 5 is not an even number, so this conjecture is false. So it says if a quadrilateral, so just a 4-sided shape, quad meaning 4, has 4 sides, it has 4 equal angles. Okay. All right. Do my best work to draw a square. That has 4 sides. All of the angles are 90 degrees. You could do a rectangle too, right? That also has all 90-degree angles. So a counterexample would be like a parallelogram. So you can see this angle is a lot bigger than this angle. So it does not have a, it does not have 4 equal angles. So that invalidates that original conjecture. So the square root of x squared is equal to x. Hopefully you're like, oh my gosh, we've done this lots. Hopefully it's true. So the square root of 3 squared. Well, 3 squared is 9. The square root of 9 is 3. So here, x was equal to 3. X squared, x. Yeah, that supports it. So a counterexample, just square root of negative 3 squared. So negative 3 multiplied by itself is equal to positive 9. Square root of 9 is equal to 3. So here x is equal to 3. Here x was equal to negative 3. And so if you're thinking back to that first unit, that's because we really only talk about the primary or principal square roots. So that's why it works out that way with that one. I'm not as wild about that particular question, but at least you can kind of come up with an example. A point lies in the second quadrant if its x-coordinate is negative. So first you need to remember how to number your coordinates. So this is actually quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So a supporting one would be a point at negative 2 and 3. So negative 2, positive 3. So that supports the conjecture because its x-coordinate is negative, it's in quadrant 2. A counterexample would be a point at negative 2, negative 3, because negative 2, again 1, 2, but now negative 3. So your negative y values take you down here. So that would be right there. And that's in quadrant 3 instead of 2. So again, just like with the last couple, I probably didn't X them out. These conjectures have been proven to not be true, right? If we find even one counterexample, that conjecture is invalid. So E, the square of a number, is greater than or equal to the number. All right. So something that supports that conjecture is like 3 squared equals 9. Yeah, so the square of 3 is greater than it, right? 9 is greater than 3. 5 squared equals 25. 25 is greater than 5, yeah. So a counterexample would be if I took 0.5 and squared it. So try punching that into your calculator. 0.5 squared, it's actually equal to 0.25. Yikes, this number is not greater than that. So 0.5 is greater than 0.25. And so same thing you would see with any sort of number between 0 and 1. So if I take 0.1, squared it, 0.01. No, this number now is greater than this number. So that is a counterexample in that case. All right, getting close. So the Fibonacci sequence is a sequence of numbers in which the sum of the previous two terms gives us the next term. So what this is saying is 1 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. So it's saying in order to figure out the next number, you need to add up the two previous numbers. So determine the next four terms in the Fibonacci sequence. So 13 plus 21 equals 34. And then it would be 21 plus 34 is equal to 55. 34 plus 55 is 89. And 55 plus 89 is equal to 144. So our next four terms in the Fibonacci sequence are 34, 55, 89, 144. So consider the following four consecutive, again, one after the other, Fibonacci numbers. So 2, 3, 5, and 8. So let me erase. No, nothing. It's doing these ones here. So 2, 3, 5, and 8. So one after the other. So they're consecutive Fibonacci numbers. It says multiplying the outside two numbers and then multiplying the two inside numbers and subtracting gave the following. So it's saying 2 multiplied by 8 is equal to 16. And then multiply the two inside numbers. 3 times 5 is 15. If I take 16 and subtract 15, I get 1. So, oh, okay, sorry. I thought it already gave me a conjecture. It says, repeat this procedure with another set of 4 consecutive Fibonacci numbers and make a conjecture. Okay, so let's do 5, 8, 13, and 21. So that is these 4 consecutive Fibonacci numbers. So again, one after the other. So multiplying those first two numbers, or sorry, the first and the last, so 5 times 21 is equal to 105. Multiplying the inside numbers, 8 times 13 is 104. If I subtract that, I get 1. So 105 subtract 104 is equal to 1. Okay, so I see that I got the same thing here, right? If I took the product of the first and the last and subtracted the product of the two inside ones, I got an answer equal to 1. So the conjecture that I'm going to make with this one, so with 4 consecutive Fibonacci numbers, the product of the first and last number is 1 greater than the product of the middle numbers. So, sorry, I'll let you kind of write that and then talk about it. I could have worded it differently. I probably should have. I could have said the difference between the product of the first and last and the two middle ones, the difference would be 1. That might have worded it better, but that one still makes sense, kind of the way I wrote it. So you can see, you can play around with it. and see if you find any counterexamples to the way that I've written that conjecture right now. So just a little summary. A counterexample is an example or evidence that does not support a conjecture. Sorry, I don't know why the word evident is there. So evidence that does not support a conjecture. I'm writing that in my notes right now. Evidence. So finding a single counterexample invalidates the conjecture. So it makes that conjecture not true anymore. So finding a counterexample will require you to revise your conjecture. And even if you cannot find a counterexample, you cannot be absolutely certain that there is not one. Right? If you tried the Fibonacci one and you couldn't find a counterexample, just based on the numbers I had, keep in mind it keeps going. You're just adding up the two previous numbers to determine your next Fibonacci number. So it would be essentially impossible to test or impossible to check all of the different possibilities for that last conjecture. So you can't be sure that there is not one. Any supporting evidence you develop while searching for a counterexample does increase the likelihood that the conjecture is true, but it doesn't show that it's true indefinitely. So you've got some textbook questions on, it looks like page 17 and page 22 to 25. Make sure you've done those things from page 12 to 14 as well. And that's it, that's all.